So now that we've talked a bit about what parallel streams can do and how it works under the hood, I'm going to also give you a few caveats about some programming hazards that can arise with parallel streams. And we'll talk first about what those caveats and problems are, and then we'll talk a bit about how to avoid them. And you'll get a chance to play around with all this stuff when you do the programming assignments, of course. So one of the big assumptions that I've mentioned a number of times is that the parallel streams framework assumes the behaviors you give it to work on don't incur race conditions. And remember, a race condition is a problem that arises when an app depends on the sequence or timing of the threads that are running in order for it to operate properly. And I always like to use the crashing cars metaphor because that's a good example of things trying to occupy the same space where they shouldn't. So it's corruption. You're smashing things together. And the same thing occurs in memory hierarchies in modern multi-core processors. So that's an assumption that the streams framework makes. If your code abides by that assumption, all is well. If your code does not abide by that assumption, as usual, chaos and insanity will ensue. So the easiest way to avoid any kind of problems is to write behaviors that don't have side effects. So avoid behaviors with side effects, don't have side effects. So what are some examples of side effects? So there's a couple examples. We'll start first with stateful Lambda expressions. And this is cases where what we pass into these operators, be they intermediate operators or terminal operators or whatnot, have behavior that depends on shared mutable state that's not protected. And even if it is protected, it's usually still a bad idea because even though it'll work in the sense that the computation will produce the desired output, it will be much slower than it really needs to be, which kind of defeats the whole point of using streams. So if you take a look at this statelessness link that's in the Java documentation for streams, it'll give an overview of this kind of thing, and I'm just going to walk through an example. So what would be an example of shared mutable state? That state that can change during the parallel execution of a pipeline that is not protected by any locks. So here's the simple example, which you can find in the EX16 folder. This is buggy factorial. I think I've talked about this before, but just to recap it. We're trying to compute the nth factorial, and of course, we'd like to do it in parallel because we hope it'll run faster. And there's a whole bunch of issues there. If you want to have some fun, go to this link and look at the code and run the code, and you can actually see the behaviors. There's a bunch of different ways to do this. But here's the buggy way to do things. So the buggy way of doing things is to make ourselves an object called total of type total. And you can see total has shared mutable state. So mTotal is a field in the total class that has the value of 1. And as you can see here, it's going to be modified by the mul or multiply method. So here's where the problems arise. So mul takes n, and it multiplies mTotal by n, and then updates mTotal. So right away, you can see that is mutable. It's changing its value. And if you take a careful look at the actual code here, we're generating a range of values from 1 to n. And then in parallel, we're going to run this for each operator that's going to apply the mul method on the single shared mutable data object t. And that's where the problem arises, because there is no locking here, because that's not what's expected by streams. Streams expects that your behaviors are stateless, but this is a stateful mul method, operation behavior. And so it's multiplying mTotal by n and updating mTotal simultaneously in multiple threads in the parallel stream. And while this instruction, mTotal times equal n, may look atomic to the naked eye, of course, it is not atomic at all, because there's multiple things that are taking place to do that operation. And even if there was only one thing taking place, by itself, it's not propagating the values through the cache hierarchy of the memory, because that's not what it's been told to do. There's no synchronizer here. So bottom line, this is bad, and you do not want to write code like this. It turns out to be ridiculously trivial to fix this by simply using reduce instead of trying to do this for each thing. So you can use a proper Java terminal operator that will make this whole problem go away, and it'll be very efficient, and you don't have to add any extra locks. Another problem that can arise with parallel streams is interference with the data source. And this can occur when the source of data the stream is using to traverse is modified within the pipeline of aggregate operations. And this is very, very subtle and pernicious. Now, the good news is, again, you kind of have to work at this to make it this kind of a mess. But just be aware that it's a problem. So let's take a look at an example. And by the way, you can read about that here in this link about non-interference. So here we create ourselves a list of 10 integers in the range 0 through 9. Those are ints, and then we box them up. So now it's a range of integers, and then we collect that into an array list. And just for fun, I used a different factory method. Usually I would just use toList, but here I decided to use toCollection, and I said array list : new. Why would you use toCollection versus toList, you ask? Well, one reason, which I didn't actually do here, would be to use linked list : new instead of array list : new, because in that case you can control the type of collection that's being created here. So it gives you a little bit more control. The toList factory method, in contrast, always creates an array list. So now we've got this list of integers, and now we're going to go ahead and turn on the parallel stream feature. And by the way, you will get problems here, irrespective of whether you had a sequential or parallel stream. You just get slightly different problems, and probably the parallel stream will show the problems faster, but whatever, there will problems occur. And what we're doing is we're going to use the peek operation. Peek is an operation that's intended to have really no side effects. It doesn't change this. It's not supposed to change the stream. It's not supposed to change the underlying collection it's being iterated over. It's just to be used for things like debugging and logging. But here, because we're being pathological on purpose, we're going to pass in the remove method, which is going to turn around and try to remove the item from the list that we're using as the basis, as the source of our parallel stream. So, of course, that's going to cause an enormous amount of chaos and insanity. And if you want to have fun, you could run this example. And let's see, this is the EX11 example. And try running it, and you'll get concurrent modification exceptions and strange results and so on and so forth, because we're modifying the underlying data source as the stream is running. So that's another thing not to do. So what should you do? Well, what you should do is use behaviors that don't have shared state. Use behaviors that don't modify the underlying data structures and data sources and so on. And if you can do that, then you don't have to provide any additional synchronization in your behaviors, which is wonderful. That's the real benefit of this whole thing, is it takes away a lot of the accidental and inherent complexities of concurrent and parallel programming. So here's an example. This is an example of a pure functions. So we have things like search results, : is empty, which just checks to see if the list has the size of being 0. So that doesn't have any side effects. And in this particular case, we're making objects using these particular capabilities. And again, there's no shared state here that we have to worry about synchronizing or being corrupted by things running in different parts of the program. So these are examples of so-called pure functions that are light as a feather. Now, if for some reason you can't do this, if there is actually shared state that needs to be manipulated or updated while the stream is running in parallel, for goodness sakes, synchronize it properly. If you can't get away from that. And there are plenty of cases where, or there are some cases where you can't totally get rid of shared state. So here's an example. For your program that you're using for the assignments, we have an image cache that's keeping track of the images that are being downloaded, transformed, and stored. We cache those things in memory. And to do that properly, we need to have that data structure shared between the various threads that are running. Now, you don't see that because we kind of hide it from you in the skeletons, but it's lurking in there somewhere. And what we do to make sure everything works properly in the case of parallel streams is we use a collection that has nice properties for concurrent and parallel execution. In particular, we use something called a concurrent hash map. And a concurrent hash map, which you can take a look at here, and there's other cool articles we'll talk about later. A concurrent hash map has the ability to be able to add and remove and find elements by different threads by using all kinds of incredibly clever optimization techniques. For example, what they do is, remember how a hash table works? You've got some kind of, or a hash map works, you have some kind of array, and you hash the value, and then the array points you to buckets, either like a linked list or a balanced binary tree or whatever. Well, what they do is they make each of the different buckets be its own synchronization point using a very cool technique called compare and swap, which is a very, very, very efficient, low-level, essentially lock-free mechanism. And so when somebody looks things up in the table, all the values that hash to different locations in the array can all run in parallel because they're not having to contend for any single locking point. So there's all kinds of other optimizations there too, but just be aware that there's cool stuff that takes place. However, it's still better if you can possibly avoid having to do any kind of sharing to avoid it, because even with all these optimizations, it's still a little bit slower to have to share stuff than it would be if you didn't have to share stuff. But when you do share stuff, make sure you synchronize it properly and try to use some clever concurrency mechanisms to make that synchronization as cheap and scalable as possible. So that's the end of the overview of avoiding common programming hazards with Java parallel streams.